So let's take a look at this problem here. So all we're doing, we're taking this polyfunctional molecule. You can see we have a couple of different functional groups. So we have an enone, which is an alpha beta unsaturated ketone. And then we have a regular ketone. Okay. And then this reagent is, we just think of it as copper hydride. But there's a ligand sticking to copper that helps it be soluble in the organic solvent. Kind of gives it some special electronic properties, but we're not going to worry about the particulars of the ligand. Right, so when we look at that reagent, copper hydride, what's special about that reagent? How does it function? What makes it unique?
Hydrogen's more electronegative.
Awesome, right? So this is going to be like any other of the hydride reagents that we've seen, where we have a copper atom connected to a hydrogen. That copper hydrogen bond is going to be polarized towards hydrogen, giving hydrogen a partial negative charge and copper a partial positive charge. Right, so we can think of this like sodium borohydride, lithium aluminum hydride, right? Any of the other metal hydride reagents where we have an electropositive metal atom connected to a hydrogen, making the hydrogen nucleophilic. Okay. Anna, do you remember what makes this, or what sets this apart or makes it unique relative to sodium borohydride or lithium aluminum hydride?
Not really.
Not really? Okay.
Yeah.
It's okay. Does anybody call that from the video?
I don't know, but I can guess.
Sure.
Maybe it replenishes some hydrogen after it uses it.
No. It's gonna be it's more of like a selectivity thing than how it reacts.
Stereo or regio?
Regio selectivity. Yeah. Sure.
According to my notes, it's selected for 1,4 addition.
Good. So this copper hydride, relative to sodium borohydride, lithium aluminum hydride, this is a soft nucleophile. Right, so when it's given the option, it's going to be selective for 1,4 addition over 1,2 addition. So when we look at the functionality that we have here, particularly in enone, right, you can see there are 4 atoms involved in that, or that make up that functional group. Right? 1,2 addition would deliver a nucleophile to carbon 2, okay, and then 1,4 addition would deliver a nucleophile to atom 4, carbon 4. Right? So when this addition takes place, the hydride is going to be delivered to carbon 4, and then those electrons will be pushed all the way up to the carbonyl. And what is generated is this enolate intermediate. And here's the hydrogen that was just transferred to the 4 position. once we form this enolate intermediate, there are kind of two options, or two things that could take place. So what options do we have? Right, we have an enolate. Just got done looking at enolates for a couple of weeks. What do they do exactly?
Also, something else we had a problem with as well.
Of the enolate, it's not really how. So what do you mean by that?
I would, like, the double bond would return and grab a nucleophile, and then the electrons on oxygen would come back down and reform the carbon, or some carbon.
So remember, enolates are nucleophilic themselves, right? So it's not going to react with a different nucleophile. Enolates are nucleophilic, basic at oxygen, nucleophilic at carbon, right? And so what reaction partners do we usually see?
Would it go into the ketone?
Good, right? And so what would that be? What type of reaction would that be?
I'm not good with names.
Come on, addition of enolates to ketones? An aldol reaction, right? Right, so we have our enolate, we have in the same reaction a ketone. So electrons will fall down, reform the pi bond, kick out the enolate alkene, right? And then make bonds to the other ketones. This is just an intramolecular aldol reaction. All right, we form our copper alkoxide. Right, so the precursor to the alcohol. Okay, and at this point that reaction is done, right? Nothing else can really take place here. And so after a proto-quench, it's going to get us to our beta hydroxy ketone product. Questions? Okay, so you can see that we're forming a 6-membered ring if you count the atoms involved in the ring formation. So make the ketone or the carbon of the enolate carbon 1, 2, 3, 4, 5, right? And then the atom that we're quenching on would be carbon 6. So that's going to form a 6-membered ring. Questions? Yep.
We didn't lose it.
Oh, yeah, just put a, I just missed it. So we know that copper hydride can do conjugate reductions of alpha beta unsaturated carbonyl compounds. Okay? So we treat this ketone with copper hydride and then follow it up with a quench. This is what we'll get to, right? So we'll be able to reduce the alkene part of that enone system. And what if we want to affect the 1,2 reduction? What reagents would we use? Joe?
Sodium borohydride in a alcohol solution,
Okay.
and cesium chloride for
Cerium.
serum.
Right, so sodium borohydride in an alcohol solution, right, so standard ketone reduction conditions, but we're adding this Lewis acidic additive. Right, and all that additive is doing is it's really sticking to the oxygen of the carbonyl and increasing the electrophilicity or increasing the reactivity of the carbonyl carbon. So when that hydride is delivered, it's delivered selectively to carbonyl carbon. Right, so this is an example of how we can get regioselectivity in these alpha beta unsaturated carbonyl systems. Right, anybody recall what this reaction's name of this reaction is? Alexis, you don't know. Good. Good, yes, this is a loose reduction. Right, names ultimately don't matter, right? But it's part of how we communicate in the field. So. Right, so questions on additions to alkenes, nucleophilic additions to alkenes, so 1,4 conjugate additions, nucleophilic aromatic substitution, yeah.
This is kind of unrelated, but like the ligand part on the copper hydride,
Yeah.
what are they made up of? So like, cause like if there's functional groups in it, how do they not react with like the system?
Sure, yeah, so there usually aren't functional groups or reactive functional groups in those ligands. So one of the reagents, or kind of the original copper hydride reagent, is a reagent called Stryker's reagent. And this just had a simple triphenylphosphine group attached to the copper. More recently, so people usually often when they're using copper hydride, they're trying to accomplish stereoselective reactions. And so the ligands that are attached to that copper are chiral ligands. So one of the more common ligands that you see used is this ligand structure looks like this. Right, so it's a diphosphine ligand. Right, there are two phosphorus atoms. Phosphorus is right below nitrogen, so it's got that really nucleophilic, or really, yeah, I guess nucleophilic lone pair that can also stick to metals. And then in this ligand, I mean that, you know, I have it drawn, so you're seeing that there are these two arine groups like this. Those two arine groups really sit either like this, right, or like that, and they would be enantiomers of one another. Okay, and then the copper is sticking to both of the phosphorus ligands. So the ligands themselves, really the only reactive part of the ligand is the heteroatom that sticks to the metal. It's not going to have ketones or other reactive functionality. Other questions? The ligand that you're making, or the NHC compound that you're making in lab, that's also a ligand that can be used for copper catalysis, that we plan to use for copper catalysis. All right. Okay, so let's move on to a new chapter, and this is going to be probably the most unique chapter that we go over, or yeah, most unique material that we go over this semester. Okay, so when we've been looking at mechanisms so far this semester, all of the mechanisms, all of the reactions that we've drawn out, all involve two electron movement. Right, and so when we draw these mechanisms, the arrows that we're drawing illustrate the movement of two electrons, right? And usually the formation of one bond and the breaking of another bond, right? So here's a substitution reaction. We're showing these two electrons make a new bond to this carbon, right? And then the sigma electrons in that carbon-bromine bond break away from carbon and go with bromine, okay? And so when we draw our arrows, these arrows represent two electrons. Each of them represent movement of two electrons. There's a whole class of chemistry that we refer to as radical chemistry. Where the mechanisms by which these reactions, or the mechanisms that these reactions undergo, are not two electron heterolytic reactions, but are one electron reactions. Okay, so this is a molecule called dibenzoyl peroxide. Right, you can see it features an oxygen-oxygen bond in the middle, all right? And the oxygen-oxygen bond is typically very weak, all right? And this one in particular has a bond dissociation energy 139 kilojoules per mole. Right, and so to give you some context, a carbon-carbon bond, dissociation energy of a carbon-carbon bond is then on the order of 350 kilojoules per mole, right? So much, much higher, right? Much stronger bond than this oxygen-oxygen bond, right? And if we were to heat this up, it would cause that bond to break apart to form two radical intermediates. Right, and the way that we would show that mechanistically, we would take that bond, right, and we would draw one arrow going to one oxygen, and then we would draw the other arrow, another arrow going to the other oxygen, right? You can see when I draw these arrows, I'm only drawing a single fishhook on the end of that arrow, right? So it's not a typical double-headed arrow like we usually see, right? And so what this means is that whenever we draw mechanism arrows, I think we went over this just a little bit last semester, right? A single or a double fishhook indicates movement of two electrons. Right? And a single fishhook indicates the movement of one electron. So we're going to have to learn in this chapter slightly different style of accounting for the reactions, right? Slightly different style of showing mechanisms. Okay, when this dibenzoyl peroxide breaks apart into these radicals undergo a further reaction, degradation reaction, where they form a benzene radical and then carbon dioxide. Right? So see if you could really quickly just draw the mechanism that accounts for that degradation.
Is that the second heat step that you have up there?
It's so.
Oh, that's.
It's all happening in the same reaction.
Why isn't it negative? Because it got one electron more.
It's not negative because there's not an extra valence electron, right? There's no formal charge because there's not an extra valence electron, right? So that oxygen here still has two lone pairs, right? And a bond. So we would say that this oxygen has both of those lone pairs, so 4 electrons. In the bond, it owns one of the electrons in the bond, right? So that's 5, and then the radical single electron would be 6. Make sense? Good, just make sure the arrow's going to the right place. The electrons there. So we're showing there's two electrons moving. Give you another 30 seconds or so. Talk to each other. Alright, let's go over this. Okay, so if we look at what we're making, right, you can see that we need a new pi bond between this carbon and the oxygen, right? We're losing the sigma bond between these two carbons, and then we're gaining one electron on the benzene ring, right? So if we're gaining one electron on the benzene ring, that must mean that this sigma bond here is breaking so that one electron goes to carbon, right? And then the other electron can go to the bond and combine with the one electron on oxygen to make that second bond, to make that pi bond between carbon and oxygen. Okay, so we would show three separate single official arrows, right, to explain how these electrons are moving, because we have two electrons in the carbon-carbon sigma bond, right, and then one electron on oxygen, and we need to show how all three move. As you can see, when we have multiple bonds breaking and forming, these mechanisms can get pretty messy, right? So we can have kind of a kind of an abbreviated way to show this as well. Right? In this case, we would just show two arrows, right? So we would show the electron on oxygen making a bond to carbon, right? And then that's going to push those electrons, that one electron over into the carbon of the benzene ring, right? So we're assuming that the other electron in the sigma bond is being used to make the double bond to oxygen. Questions about this? Matthew?
It seems like they're going in different directions, the single electrons, is that one?
Which single electron?
Like
Here?
whenever you're breaking and forming a bond, they always go into different ways, if that makes any sense?
So that's a good observation, right? So this is what we call bond homolysis. Right, so when that bond breaks, one electron of the bond goes one direction, the other electron of the bond goes the other direction. We're used to seeing, right, whenever we're, to this point, whenever we draw mechanisms, we're used to seeing both electrons in the bond go to the same atom, right, or go to form a new bond, going in the same direction. Here in radical chemistry, when those bond breaks, those electrons go in different directions. Good observation. Other questions? Alexis? Yeah.
Would the pi rules change much with this? Like having the single electron kind of you know, like, whenever we would draw out, like, oh, this is how it transfers, would it look the same?
Guess I'm not fully understanding your question.
Like, on the carbon and the or oxygen, we have, like, the pi orbitals, like, that we can draw on the upper and lower.
Yeah.
P orbitals,
P orbitals, yeah. So you're asking like where that electron exists?
Yeah.
In what orbital? Yeah, so that's a really good question. So in this case, the electron would exist in a p orbital. That single electron would exist in a p orbital. And that's so it still can be in conjugation with the pi system. Right, so we'll go over this in just a second, but the stability rules for radicals largely follows the stability rules for carbocation ions. Right, so they can be stabilized by hyperconjugation, they can be stabilized by conjugation, and therefore need to be in the appropriate orbital to undergo conjugation or be in conjugation. Good question. All right, so here's a reagent that you will also see a lot this chapter called AIBN. And again, just like with dibenzoyl peroxide, if we heat this up, we're going to create a radical, right? Two radicals. And nitrogen gas. Right, so see if you could figure out a mechanism that explains that formation, that homolytic cleavage of sigma bonds, right? Formation of the two radicals, and then nitrogen, molecular nitrogen. Keep in mind, molecular nitrogen, looks like that bond between the nitrogens. All right, so what is this mechanism going to look like? We can describe what's going on.
The carbon and the nitrogen would break
that bond there?
Yeah, and one would go on carbon and one electron on nitrogen.
Good, alright, so we can show that this carbon-nitrogen sigma bond is breaking, one electron will go to carbon, one electron will go to make the nitrogen-nitrogen, second nitrogen-nitrogen pi bond, right? And then we would show the other bond doing the same thing. Okay, so that would be the full mechanism where we're showing all 4 arrows, right? We can also show this mechanistically in an abbreviated way. Just by showing those 2 arrows, right? And understanding that when that bond breaks, right, if one electron is going this way, then it's assumed that the other electron is going the other direction, or staying with the atom that it's bonded to. Right? And that's going to get us to here. So both of these molecules, the dibenzoyl peroxide and the AIBN, they're both considered radical initiators. Right? And they're going to be some of the reagents that we use to start radical chain reactions. So these reagents are going to be unique to this chapter. We're not going to really see them anywhere else in organic chemistry other than in reactions that involve radical chemistry. Questions? Okay. Well, then, oh, yeah.
Why does it only make one of the electrons and not both?
Sorry, say that again.
Why does it only make one of the electrons and not both?
Why do the electrons move in this way?
Yeah.
So it's more of just thermodynamics of what is being made, right? So this is, nitrogen is going to be really stable. And so this is kind of the only way to make nitrogen and form 2 stable radicals, right? If you can imagine that if we're using 2 electron movement, so I'll use this as an example here, 2 electron movement, we would make nitrogen, that's good, right? But in addition, we would make a kind of an enolate, right? An enolate of a nitrile. And that's good, that's relatively stable. But on this side, we would create this cationic intermediate, right, which is really going to be high in energy, really, really unstable. So going 2 electron movement, right, we create nitrogen, this relatively stable intermediate, but this is pretty bad, right? That's going to take a lot of energy to create and sustain. And so by creating 2 radicals that are relatively stable, then it's just a more thermodynamically favored pathway. Does that answer your question? Joey, do you have something to add?
No.
Right, any other questions before I let you guys go? Okay, good luck on the exam this weekend. See you Monday.